Hello again, everyone, and welcome back to the Block 74 Apollo Guidance Computer series of videos I'm putting together to document this project I'm working on. Today, we're going to talk about the B and C registers of the Apollo Guidance Computer. In previous videos, we talked about the guidance computer as a whole, talked about specifically the structure of how registers or the elements that store data in the computer are organized. And in the last video, we went into much more detail around the Z register and kind of how we would design and implement that. So in some ways, the B/C register is simpler, and in other ways, it adds some more complexity. Uh, like I said about the Z register, and in fact, just about every register, each one has its own little quirks and little extra features or capabilities that the designers added in order to make the computer more capable in or simplifying certain instructions as it executes. So we have as we talked about last time, we talked about the Z register, and that is part of what they call the special and central registers that have this addressable register service, which adds a little bit of complexity. Today we're going to be talking about the B register, which is not one of these kind of special and central registers, so it doesn't have the addressable register service that we talked about in the last video, but it does have a few other things, and we'll find out as we go along. As with all of the kind of the registers, the way that they're laid out, you've got the actual B register or buffer register, which is where the data is stored. And then there's logic that determines how data gets loaded into that register from the write line bus. And then there's also logic that determines how data gets read out of the register onto the bus as well. So let's look at the B register or the buffer register. Now you'll notice that I keep calling it the B/C register. And that's because they've basically combined two bits of functionality into the B register. So for the most part, we can see it's primarily a storage element, and it stores order codes and relevant address information to be executed next, right? So this is often used, like for example, if the computer goes to execute a subroutine and needs to store an address that needs to come back to, it can use this particular register to store some of that data, as well as a few other scenarios. Now, most of that is again very similar to how data gets written in. There's the write timer signal, which we talked about last time, and then there's the WB control pulse, which is the B register write enable. So this is how data gets read or written into the B register. You'll notice that there's no direct or addressable memory addressable service like we saw with the Z register. So the logic to write in is actually quite simple. And you can see here with the kind of the circuitry for the B service, you've got that WB signal, that control pulse, as well as the write timer, and then that's all. In this, you can actually see these are a whole bunch of just NOR gates that have one input, one output. So in this case, they're really just acting as an inverter and a buffer, right? So they basically provide buffering to support the kind of capabilities of the loading. We also have that control timer that we had talked about before. Again, we're not using the control timer because we're not using discrete flip-flops that they used in the Apollo guidance computer. We're going to be using the D register chips that we can write into in a very controlled fashion, but we will have kind of a general reset that we'll use in order to clear everything within the system. Now, where the B/C register gets a little bit more complex is on the write side. And because there's a couple different ways that data can be written out or sort of read out of the register and onto the bus. So one is just the regular RB. So that's the B register read enable. So this is the signal to push data out onto the bus. But we also have this signal called RL10BB, which is the B low byte read enable. And you can kind of see here that basically this reads out bit positions 1 through 10. So if we get the RL10BB signal, It's only generated during certain instructions to place the 10 low order bits of B onto the right lines. Now, there's also one called RC. And so you say, well, would that be the C register? And the C register read enable is how you'd push data from the C register onto the write bus. Now, the thing is that the C register doesn't actually exist. There is no unique or discrete C register. What the RC does is it gates the complement of register B onto the right lines that's required during certain instructions. So we talked about in kind of the overview is that the Apollo guidance computer uses ones complement for negative numbers. And that means that it basically inverts all of the bits to represent a negative version of the number. So, 0001, the negative of that would be basically just to flip all the bits. So it would be 1110. Now this ends up with kind of the weird that you get a negative and positive zero, right? So zero is going to be all your bits set to zero. And then if you flip all those bits, you actually get negative zero. So it's not, it does add some complexities in how math is performed, or, how you deal with positive and negative zeros. But it does simplify other logic in that it's very, very easy to take a number and get its negative by just simply flipping all the bits. And that's what the C register is used for. So basically, when you have to do things like subtraction, you can very easily take a number, put it into the B register, read it out of the C register, and add it. And effectively is you've taken the, 5, for example, if you load 5 into the B register, then you read it out of the C register, you now have negative 5. So if you add that to whatever number that you had, you effectively have done subtraction. And that's kind of how, this kind of feature simplifies some of that within the Apollo guidance computer. So that means that the kind of the read logic is a little bit more complicated, in that we've got, this RC where we have to say, okay, now we need to read out the complement, and then this, RL10BB where we basically have to say, only read out the low 10 bits and discard the high 16 bits. So let's flip over to the actual design of the B register here. And you can see, that it looks like, we've got a bit more, a little bit more complicated here. So let's go into this and to see kind of how we've implemented it. So the first is we've got our 4 74LS173s. These are our 4-bit D registers that actually store the data. This is kind of the B register itself. And then normally we've got 2 of our octal transceivers here that would read the whatever contents of the B register out onto the bus. Now, because we also have this kind of C or pseudo C register that inverts all of the bits, we have another set of octal transceivers that invert. So we've got a whole bunch of inverters on each of the data lines that will basically flip those bits to create our pseudo C register and read that out appropriately. So what we have here is we've got both of our, when we to read data in, it's very, very simple, right? We've got our write timer that we've buffered, and that collects for our clock like we do in the Z register. And then for the actual write data in, it's super simple because, all we have is the WB pulse. And because, yes, this is negative logic, and the chip enables are negative logic on these D registers, it's very simple. We just take our WB and we connect it all to our 4 registers to read data in. Now, reading it out on the flip side is a little bit different, and it's kind of similar to what we talked about with the Z registers. We've got our read timer, and we invert that, and then we NOR that with our write B signal, or we NOR it with our right C signal. And in the case of the right C signal, we flip that one more time to actually take that. You can see it kind of follows all the way over here to our transceivers, where we will then enable through our chip enable these two transceivers to push the complement or the inverted contents of bus B out as a RC read signal. On the RB side, we've got kind of a similar that we have the data coming out, but again, we also have this this RL10BB signal, where most of the time, if it's the low 10 bits, we just want to read them out normally. So we've got our little, we NOR that together with our RL10BB signal. And then for most of these, the lower 10 bits, we just use that as our chip enable, write them out, and away we go. Now, we also have to do as well, how do we deal with this RL10BB to do with, well, there's 11, 12, 13, any of the high order bits that shouldn't be written out. And that's where we've added these additional AND gates, where basically the logic is that if we have this RL10BB signal and we're in the read timer so that we're being expected to read it out, we'll combine that together, and then we have to flip it so that we get the signal that we want. And in this case, we're going to just put a bunch of AND gates together. And because if we have the RL10BB that's asserted during write, this will actually be a 0, so this will be low. And by going into an AND gate, if we set one of the inputs of an AND gate to 0, we're always going to get a 0 out. So that means that if this RL10BB is asserted, we will just write zeros into the 11, 12, 13, 14, 15, and 16 bits. Otherwise, this will be a 1. So that means we'll read out whatever the contents of the register are. So if it's not asserted, and that means, again, because of the negative logic, that RL10BB is going to be a 1, we will just write out whatever the contents are of 11, 12, 13, 14, 15, and 16. So that kind of is the design of the B/C register. And I'll just quickly pop into our little simulator here. And we can see on the read side, it's fairly similar. So let's zero everything out. So we've got our cleared registers. So this is just, we've kind of simulated here a WL10, or sorry, WL01 and WL11. So that would be our B01, our C01, our C11, and our B11. So if we look at, if we have zeros, because C is always our complement, so it's inverted. But if we need to write data into the 1 or the 0, right now, because our WB is a 1, it's not asserted, so we're not going to write anything into our registers. At the moment I click this, now we're going to load data in, and then we can see our B and C flip. So we've got a 1 in our B01, so C is 0 and B is 1. And in our kind of simulated 11, we've got a 1, and then we've got a 0 or 1. Now, on the read side, because we have this, normally if I don't assert these and I click the button, we're not going to output anything, so there's no control. If we do just a regular RB, and I hit the button here, you can see this is our kind of read enable on that we will send to our octal transceivers to allow data to be released onto the bus. We can see how that works. If it's on the RC side, we have the RC, so that's going to connect to that second set of octal transceivers to push data out onto the C bus. And then if we have our RL10, we will see two things will happen. One is we will send a 0 to our B transceivers so that they'll push data out onto that bus. But we also have our B11 that when it's asserted through those AND gates, will actually, in this case, write out a 0 because we don't want to read out those high bits out onto the bus. So how this has been implemented And see, here's a picture, and that's what actually I'm going to do in the next video is show you how I've actually assembled and built a few of these. That's my B. Excuse me. This is the BC register and how I've laid that out. And if we look at kind of the components that have gone into this, we have four 74 LS173s. This is our our four D-type registers, each one that have four, so that's our 16 bits. We've got our four 74 LS245 octal bus transceivers, so we have two for to read out the B contents and two to read out the C contents. And then we've got four 74 LS04 hex inverters. So these are inverters, and we need a bunch of them because we have to invert all 16 bits in order to create our pseudo C register. And then we have one 74 LS02 for 2-input NOR. And then we've got two 74 LS08 quad 4-input, or sorry, quad 2-input AND gates that we use to kind of zero the high bits. And then we have our buffer that we're using for the, just to make sure that we've got enough fan out capability for our clock and our reset. As with others, we've got our 16-bit or 16 red LEDs. Now, the one thing is, because the boards that I built only have the 16 LEDs, I've wired this to only show the contents of the B register, so we don't have the inversion or of the C register that's also showed as a separate kind of set of LEDs. And that's fine because we know that the C register is basically the opposite of whatever we show here. So if it's on for the B register, it would be off for the C register and vice versa. Then of course we've got capacitors for each and every chip, and then we've got the connector. It's not actually soldered on in this picture here, but we'll show that shortly. Anyone, this has been a bit shorter compared to our previous video on the Z register, but the next one we're going to show the actual construction of one of these. But as always, if you like what you see, please subscribe, and always looking for feedback. Whatever you think will make these videos better, please let me know, and we'll see you next time. Thanks.